Problem 7. An air-filled capacitor consists of two parallel plates, each with an area of 7.6 centimeters squared, separated by a distance of 1.5 millimeters. A 25-volt potential difference is applied to these plates. Calculate the electric field between the plates. Okay, so let's draw a picture. Oh. Okay. I like my rectangles a little thicker. There we go. There we go. Take a pen. Let's make it blue. Because everyone likes blue. Actually, I wonder if that's true. What if anyone's ever like, nah, blue, I hate blue. Worst color ever. Probably not. All right. So there's the photo. And we want to convert. So we know voltage equals negative E dot dr. And since the electric field is constant, we pull it out. And then the integral becomes E dot dr. E times d, where this is the distance d. So now the electric field will be negative voltage divided by distance between the two. Which actually makes this really, really easy. So then we have 25 over 1.5. And I think they're just looking for a positive answer. So, 25 divided by 1.5 times 10 to the negative third. I said 15, didn't I? I'm at 1.5. There we go. And that's going to be, I'm going to say 17,000 kilovolts. Or 17 kilovolts. Here we go. 17 kilovolts per meter. Okay. Probably should write that over here so I don't forget it. Times 10 to the negative third equals 16.7 times 10 to the third kilovolts per meter. Okay. Calculate the surface charge density. Okay, we can do this. We know from previous studies in Gauss's law that E equals 2 sigma, sigma over 2 epsilon naught. This is probably a formula that you'll be given, but I'm going to look this guy up just to make sure I'm right. Electric field due to an infinite plane. There we go. Infinite line charge? Nope. Flat sheets, as opposed to wrinkled sheets. Too slow. Maybe if I just click images, the right thing will pop up. Yep, E equals sigma over 2 epsilon naught. Perfect. And epsilon naught is 8.85 times 10 to the negative 12th. Okay, so we know what the electric field is. So we're going to have surface charge density, which is sigma, is E times 2 times epsilon naught. All right. Now, the catch here is okay, let's do this. Make sure I'm not doing anything terribly wrong. So this is the electric field due to two plates. One on the left, one on the right. But what I'm doing here is I'm using the surface charge density for just one plate. So to do this, I'm going to have to divide it by 2. And this is going to be E times epsilon naught. There we go. So I already have E right here. So I'm going to multiply it by epsilon naught. 8.85 times 10 to the negative 12. And this gives us negative, where did that negative, 2. So we have, that's pretty small. Let's see what they're looking for. Nanocoulombs. Okay, yeah. So I'm going to say 147 nanocoulombs. 147 nanocoulombs per square meter. There we go. That seems almost reasonable. Bam. Okay. So, and the trick there is going to be the dividing by 2, because right here, this is the electric field for a single plate, but we want to find but we're taking into account the electric field from both plates. So I have electric field from both plates because they're both adding together. The pluses are creating electric field this way, and the minuses are creating electric field going to them. So the two will add up together. So the electric field is actually due to both plates. And so then we find the surface charge density. We're going to find the surface charge of this guy and the surface charge of that guy. It's as if it was a plate twice as big, except these guys are negatives. So we take the negatives, break it off, flip it over here. That's the idea. Calculate the capacitance. All right. So not really sure where we're going here. So, all right. Ooh. I was going to write a Q, but I'm going to make that a C now. And that's a terrible Q. Q over V. All right, so we know the surface charge density, 147 times 10 to the negative 9th coulombs per square meter. And then we know that we have 7.62 centimeters squared. So now I'm going to convert this centimeters squared, that is awkward and terrible, to square meters. Now the thing is, normally you multiply by 100 to change centimeters to meters. Well, we have two sets of centimeters here, so we're going to have to divide by 100 twice. So we're going to have two 10 squareds on the bottom, which will turn into 10 to the 4th. And that's because we have the centimeters squared. Okay? And that will give us the charge. So what we have is a surface charge density. Surface charge density is charge per square meter. We multiply by square meters, we get charge. And we need to divide by the voltage, which we know is 25. 25. Yeah, I can write that better. 25. Okay. So this is our surface charge density. We need to multiply it by 7.62. 7.62. All right. Divide by 1,000, and then also divide by, what was the 25? And I'll look and see if I actually put this in right. So this is the surface charge density. We have 7.62 on the top. I want that on the, I want that on the bottom. Nope, I don't want that on the top. We're dividing by 1,000. Nope, yeah, but I think they did some. There we go. Maybe this guy will straighten it out. All right, got the 1,000 on the bottom, got the 25 on the bottom. Have a 1.5 times 10 to the negative third. That's probably from the previous. Yeah, I'll assume that's correct. And we get 4.5 times 10 to the negative 11th. Bam. Which is 4.5, 45. 45 picofarads. Calculate the charge on each plate. Okay, we can do that. We know the capacitance, so we could go back and do it the way we found it earlier up here. But I'm just going to do it this way. So I'm going to do C equals Q over V. We already know, therefore, Q, the charge on each plate. It's not the total charges together, and it's not the absolute value of the charges either. It's just the charge on each plate. So if one is, 20 microcoulombs on one, it'll be negative 20 microcoulombs on the other. Q equals capacitance times voltage. We already have the capacitance here, and we know the voltage is 25. So what I'm going to do is I'm just going to take our answer that we had from capacitance. There's probably some way to simplify this. Don't even care. Don't even care. I'm going to make Wolfram do extra work and not even worry about it. All right, so we got a nano answer. Okay, so it's going to be in 1,000. So 1,124. 1,124 picocoulombs. 45 times 25. 25 volts? Yep. 1,125. Okay, yep, seems reasonable. Okay. And that will be the charge on each plate. Yep. So the best way to go through this, so when you start off with most of these electrical problems, you use common sense and reason to try and work your way through them. Once you start getting to this point, you're moving away from reasoning on them out and just knowing the formulas. It's like, hey, here's this formula. It kind of has some of what I need. Here's this formula. It also has something that looks like I might need. You throw it in a box. You shake it around with algebra or integration or whatnot, and you see if what you need comes out. Excuse me. I know that's not the best way to go through life, but sometimes it's your best bet. So that is how I would recommend doing this problem. Hope this helped. On to the next problem, number 8.